Okay, we have here today an integral suggested to me in the comments by Sable8172. We have the integral from 0 to 2 pi sine x to the 25th times sine 17x dx. And I know two ways to do it. The only problem is the first way is kind of horrible. What we would do is we definitely have ways to reduce the power on sine 25th x because we know sine squared x is going to be 1/2 1 minus cosine 2x. So we could break up the sine to the 25th over and over and over again. And then with this, we can use like a different angle formula with the cosine 2x. Of course, we probably have to reduce power again. The trouble with it is it's just super tedious. I didn't even try it, but I feel like we'd have to reduce like 10 times. And so I didn't want any part of that. The method I think is going to work nice is what we can do is use King's principle on this, just noticing with the upper bound of 2 pi, we can start by reducing that. Okay, now we have our Queen's principle over here to the right. Notice we've got two different formulas. And looking at it, comparing it to our integral where we're going from 0 to 2 pi, in Queen's principle for both these we're going from 0 to 2a. So what's going to happen is the a value on this is just going to be pi. And then at the same time we can use the tic-tac-toe board, because you can see no matter where the x guy and they're the o guy, and no matter where the o, like if he goes here, the problem is we still win. But if he blocked us here, we'd still win over here. And that's the way Queen's principle works, because no matter which version of the formula we use, it's going to solve the integral. So what we're going to need to find is this f of 2a minus x value. So what we want is, if this whole thing here, this is going to be our f of x, then for f of 2a minus x, we want f of 2 pi minus x. Now for just thinking about sine of x, we know if we shift sine by 2 pi, if we had x minus 2 pi, this is just sine of x. Sine's an odd function and we reverse the sign. So when we do this, we end up getting minus sine x. So on the sine 25th x, we've got an odd power. This piece is going to be minus sine 25x. And then for sine 17x, it's going to kind of work the same way. What's going to happen if you did this with like the different angle formula, this is going to be the same thing as minus sine 17x. But here minus times minus is plus. This is the same thing as f of x, so we end up getting back f of x. So looking at our formulas, this one didn't work. That would be the real easy way. If we could just say it was 0, we'd be done. But this second check here is going to work. One thing I should say before moving on, I hope I didn't fool anyone with the tic-tac-toe board, because it won't always be one or the other. Sometimes you do this, you might get something else. It's just that it tends to work nice with like sine and cosine. With the like supplementary angle formula with 2 pi, is you almost always get like the same thing back or something with a minus on it. Okay, so now that we've gotten through all that nonsense here, we can just kind of apply this down here at the bottom and rewrite this. In a way, it seems like a lot of work just to pull a 2 out from the integral, but it's actually worthwhile. And also, when you're doing it on paper, you could probably just do it by looking at it. So a lot of people can do this in their head. So it's really actually a pretty good deal. And now the integral is going to stay the same. It's still going to be just this f of x. And now at this point, we really have the same problem. We still need to reduce this whole thing. But now with this form here, we can actually use the reciprocal beta function to solve this. Okay, now for reciprocal beta function, we have this formula right here. Just note, you could have, think about if you had something different, if you had like a cosine here or you had 2 cosines. There's formulas for each of those. There's 4 combinations, right? So there's going to be a reciprocal beta function formula for each of those, really similar to this. To apply this here, we're just going to need to find our x and y value. So for the y value, it's just going to be on the sine. So we have our y, and this formula is going to be 17. For our x, we can just kind of rearrange this slightly, write this as 26 minus 1. So our x value here is going to be just 26. And then for the formula on the right, it's not too bad. We just have to deal with, we get kind of a messy expression on the beta function, but just remember to reduce, for the beta function, we can express that in terms of the gamma function like this. So we just kind of need to add up our x and y values and kind of go to this right here. Then from there with the gamma function, we can express things in terms of the factorial. We can use this formula. For the gamma function, we can write it as, actually, we don't really need this one. We actually need to do it. Actually, let me get rid of this because we don't really need this. It's not, I don't think that's going to be helpful here. What we need is to do it in terms of factorial. We can use this one. So what we'll do is we'll go straight to the formula on this. We've got the 2 up front. Then it's going to be pi sine our y value 17 pi over 2, then 2 to the x minus 1, so that's going to be back to the 25. So we have 2 to the 25 times x, which is 26. And I hope there's no confusion. I know we're using x here, but we've got x as the input on the beta function, so a different x. Then with the beta function, x plus y plus 1, that's going to be 44 over 2, or 22. And then here, x minus y, that's going to be 9 plus 1 is 10. So our second value is going to be 5. Sine of 17 pi over 2, you can think about if it was 16 pi over 2, that would be sine 8 pi. So like we're starting the circle over again. So this is actually the same thing as sine pi over 2. And so this piece is just 1. So then we'll just continue and simplify. So now what we're going to have is 2 pi, just putting this together, 2 to the 25th times 26. And then we'll use this right here where the z1 is going to be 22 and the z2 is going to be 5. So let's see, extend this. We're going to get gamma of 22, gamma of 5, and then we'll flip it and bring this part into the numerator and sum them, so it's going to be gamma of 27 here. Putting in terms of factorial, this is going to be 2 pi times 26 factorial, 2 to the 25 times 26, 21 factorial, and this is going to be 4 factorial. Now for 26 factorial, let me kind of expand that out some. What we can do is write it as 26 times 25 times 24. Not really sure if I want to do this, but we'll keep going. 21 factorial. So then now I can cancel 21 factorials here. I can cancel 26 here. 4 factorial is 24, so I can cancel one of these here. I think I want 22. I mean, you could at this point you could simplify it a million different ways, I guess. But for 22, I'm going to write that as 2 times 11. So then let me try to clean it up a little bit. 23 times 11 is 253 times pi. And then 25 times 2 times 2, 25 times 4 is 100 over 2 to the 25. So putting this together for my final solution, we get just 25300 pi over 2 to the 25, and that's it. And I was thinking some people might not like this form just because, we could do, we've got 2's here, we could do some more cancellation. On Wolfram Alpha, they have this reduced further to 6325 pi over 8388608. So this way is further reduced. I don't know, I kind of prefer to have 2 to the 25, but maybe it's just a taste thing. And this thing approximately on Wolfram Alpha is going to be 0.0023688. Anyway, I thought it was pretty nice. We really didn't have to do any integrations. It really just came down to simplifying these numbers, and that was really all the work. Let me know if you had different ways to do it. I didn't think about too much. It just seemed like the reduction would be tedious, but maybe there's some shortcuts in that reduction. Like maybe some of the integrals end up being 0, and it's not as bad as I thought. So that's it for today. Thanks so much for watching. Have a good day.